Okay guys, so I'm going to briefly go back through the examples from today just so that you have them saved somewhere. So the first example I did was example 8.1 on page 351. So that example was a freelance computer network consultant is employed only when she has a contract for work, and each of her contracts is for 1 week of work. Each week she is either employed or unemployed. So there's my state 1 and state 2. And her records support the following assumptions about the conditional possibilities. So A, if she is employed this week, then next week she will be employed with a probability of 0.8 and unemployed with a probability of 0.2. B, if she is unemployed this week, then next week she will be employed with a probability of 0.6 and unemployed with a probability of 0.4. The problem is she is employed this week. Find the probability that she will be employed 2 weeks from now. So let's start with the fact that she is employed this week. From there, next week, she could be either employed or unemployed. So this is next week. From there, she could be employed or unemployed the following week. Okay, so the probabilities of those. They told me that if she is employed this week, then she will be employed next week with a probability of 0.8. So that same thing happens here. If she's employed this week and then employed again, that probability was 0.8. If she is employed and then unemployed, that's a probability of 0.2. So same thing in this situation. She was employed and then unemployed. That's a probability of 0.2. Then if she's unemployed, then the following week, probability of 0.6 that she is employed. So 0.6 there, which means this has to be 0.4. Okay, so then I went ahead and found each of those separately. So this would be 0.64 if I multiply these two. If I multiply these two, that's 0.16. If I multiply these two, that's 0.12. And if I multiply these two, that's 0.08. And they wanted to know what is, or find the probability that she will be employed 2 weeks from now. So here, this is 2 weeks from now. They want to know when is it that she will be employed. And that's those two cases. So 0.64 was the first option, 0.12 was the other one. So total, that gives me a probability of 0.76. Okay, from there, I talked to you about what a transition diagram and a transition matrix was. So first, let's talk about that transition matrix. So I like to create kind of a table to look at with all of my possibilities. So employed and unemployed, employed and unemployed. What happens if I'm employed and then the following week I'm employed again? That was 0.8. What happens if I'm employed and then unemployed? That was 0.2. So this row right here should add up to 1. If I'm unemployed to begin with, and then I become employed, that probability was 0.6. If I'm unemployed and I remain unemployed, that probability was 0.4. Again, that adds up to 1. So if I'm just looking for my matrix, so this is my transition matrix, that would be 0.8, 0.2, 0.6, 0.4. If I need my transition diagram, My transition diagram is that weird looking diagram that we talked about. So remember, you have two states in this case. I've got a state of employment or a state of unemployment. Sorry. Okay, so my first state is employed, my second state is unemployed. And then I need to know what's happening between these. So this is where all those arrows come from. So let's say I start out as employed and then I end up back at employed again. That probability is 0.8. If I am employed and then unemployed, that probability was 0.2. So that comes from right here. Employed and then unemployed was 0.2. If I'm unemployed, so starting here, and then employed the following week, that probability was 0.6. If I was unemployed and I continue to be unemployed, that was 0.4. So this is your transition diagram. So your Markov chain, these are basically, this whole process is the process of a Markov chain. Specifically, I feel like this right here is kind of the line of thinking on a Markov chain, and then these are just ways to represent that information. Okay, then I talked about number 9 from the book. So let me get to that one and show you what the actual problem was first. So the problem is here. Number 9, right here. So a Markov chain has the transition matrix P shown below. Find the transition diagram for this Markov chain. So they gave me this as my matrix, and they want me to give them the transition diagram. Okay, so let me show what I got from this. So I'm going to write out, so here's number 9. And I'm going to write out the matrix that they gave me so that I can have those two things closer together here. So I'm just going to write it out real quick. 0.5. Okay. All right, so there's that matrix. And I would kind of make this into that table so that I can kind of see this thinking. So here's my state 1, state 2, state 3. And I don't know exactly what those are, but it doesn't matter. So here's my state 1, my state 2, my state 3, if I'm looking at this as a table. So what I would do is write those into kind of a triangular pattern so that it's easier for me to show those arrows between. So if I'm at 1, right here, and I'm going to continue to be at 1, so I'm at 1, I'm going to continue to be at 1, that's a 0.5 probability. If I'm at 1, and then I'm going to go to 2, that's that arrow right there, that is a probability of 0.4. If I'm at 1, and then I'm going to go to 3, so 1 to 3, that's a probability of 0.1. Then I would go on to the second one. So now I'm starting at 2 for all of these. If I'm at 2 and I'm going to go to 1, that's a 0 probability. So I'm just not even going to write that one in. If I needed to, I could put an arrow going that direction, but I don't need to in this case. Same thing with 2 and staying at 2. I don't need that arrow because the probability is 0. If I'm at 2 and I'm going to go over to 3, if I was at state 2 and I went to state 3, that's all 100%. So 1. If I'm at 3 and I'm going to go to 1, I'm starting at 3, going to 1, that's a 0 probability. So I'm not going to write that one in. If I'm at 3 and I'm going to 2 next, so from 3 to 2, that one was a 0.5. And then 3 and staying at 3, that was also a 0.5. So that's what that transition diagram looks like. Okay, number 13 was the next one. So 13 was right here. So a Markov chain has the transition matrix given in exercise 9. So luckily I already have that one written down. On the first observation, it is in state 1. In what state is it most likely to be on the third observation? So I need to do it 3 times. So on the first one, I know that I'm in state 1 is what it said. So I'm in state 1 to begin with. From there, I could either be in state 1 or in state 2 or in state 3. From those, so this is my first one, this is my second one, my third observation, this is where I can stop. I can either be in 1 or 2 or 3. Same thing with this one. I can be in 1 or 2 or 3. Okay, so there's my table. I've written all of that out, but now I need to fill in those probabilities. So if I'm at 1 to begin with, and I go to 1, that's a 0.5 probability. If I'm at 1 and I go to 2, that's a 0.4 probability. If I'm at 1 and I go to 3, that's a 0.1. So this one would end up exactly the same as this one did. So 0.5, 0.4, 0.1. This one, I'm starting at 2 right now. So I'm going to start here in this line. The probability of me being at 2 and going to 1 was a 0 probability. From 2 to 2 was a 0 probability, and from 2 to 3 was 1. Last one, if I'm starting at 3 and I go to 1, that's a 0 probability. 3 to 2 was a 0.5, and 3 to 3 was a 0.5. So now I'll find each of these separately. And my job is to figure out which of those is most likely 1, 2, or 3 to end on. So I need to find each of these and then figure out what my total probability for 1 would be, and then my total probability for 2, and my total probability for 3. So this first one, 0.5 times 0.5 is 0.25. 0.5 times 0.4 is 0.2 or 0.20. 0.5 times 0.1 is 0.05. Be careful with your decimals. This one's nice because it's a 0. Same thing with this one. 0.4 times 0 is 0. 0.4 times 1 is still 0.4 or 0.40. You can think of it that way. 0.1 times 0 is 0. 0.1 times 0.5 is 0.05. And 0.1 times 0.5 is 0.05 again. So be careful with this one. I feel like we get so used to doing 0.0 something that when it's 1, a whole 1, that just stays the same, 0.4. All right, so for the possibility of ending on stage 1, or sorry, state 1, this one was 0.25, this one was 0, and this one was 0. So 0.25 is the total. State 2 was 0.20, 0, and 0.05. So total, that's 0.25. And then state 3 was 0.05, 0.4, and 0.05, which is 0.5 or 0.50. So that means state 3 had the highest probability. Okay, the next one I went through was number 19. So number 19 had a pretty hefty problem with it. Let me see if I can get this to where you can see it. Okay. So people living in a small town are classified according to employment into 3 groups: industry, small business, and self-employed. So here's the data in the table. I'm just going to go with that. Let's see. A wants me to identify the appropriate states. So that first part is pretty easy since they already told me. I'm going to start this one, though, by making a table with that information in it. It's just easier for me to see that way. So I know I'm doing industry, small business, and self-employed. So that's how I'm going to label them: industry, small business, self-employed. So they told me in the table right here that if you're in industry and then the following year you are in industry again, that's a 70% chance of happening. So I'm going to call that 0.7. Industry and then small business would be 0.2. Industry and then self-employed was 0.1. So that's where my numbers are coming from in this table. Okay, so small business, it was 0.3, 0.5, and 0.2. And then self-employed was 0.3, 0.3, 0.4. Okay, so part A, let's go into what they actually asked me now. So part A asked me what my states were. Well, my states were industry, small business, and self-employed. Okay, so part B, they were asking me to do the transition diagram. So I would start out on that one with my industry up here, maybe, my small business over here, and my self-employed over here. So I'm just going to go through each of them separately. Industry, and then industry, so right back to itself, was 0.7. And then industry to small business was 0.2. And then industry to self-employed was 0.1. Small business to industry, this direction, was 0.3. Small business to small business, right back to itself, was 0.5. And then small business to self-employed was 0.2. Self-employed to industry, so this direction, was 0.3. Self-employed to small business was 0.3. And self-employed right back to itself, self-employed was 0.4. And then part C just asked me for the matrix, which I really already had in my table over here. I'm just going to make it look more like a matrix. So equals 0.7, 0.2, 0.1, 0.3, 0.5, 0.2, 0.3, 0.3, 0.4. Okay, last one was number 23, which is back over here. So this is that weird restaurant question. So a student eats in a restaurant every Sunday evening. Each week she chooses among Chinese, Greek, and Italian food. So those are my 3 states. So I'm going to start with that. I'm going to go ahead and make a table just to get myself wrapped around this problem here. So I've got Chinese, Greek, and Italian food. You can't even see what I'm doing. There we go. And then this way, Chinese, Greek, Italian. Okay, and then in this problem they said she never eats the same kind of food for 2 consecutive weeks. Well, that tells me that I can't have Chinese and Chinese. I can't have Greek and Greek. I can't have Italian and Italian. So those are all zeros. Okay. Okay, then she says if she eats at a Chinese restaurant one week, then she is twice as likely to have Greek food as Italian food. So if I'm starting with Chinese, I'm twice as likely to have Greek than Italian. So I always put that as I've 2 times the opportunity compared to 1 on this one. So then I come up with my total. This row right here has to equal 1. So if I'm making these fractions, 2 plus 1 is 3, so these have to be thirds. Okay, then if she has Greek food 1 week, then she is equally likely to have Chinese and Italian the next week. So if they're equally likely, it's 1 to 1. 1 plus 1 is 2, so that gives me a half for each of those. The last one, if I start out with Italian, if she has Italian food 1 week, then she is 5 times as likely to have Chinese as Greek. So Chinese is 5 times as likely as one of those. 5 plus 1 is 6, so this has to be sixths. And in that one, they just wanted me to come up with the matrix, which I pretty much did already. So I like having these labels on the outsides, but then that means I have to go back and make this a more formal matrix. And that's it. All right, hope that helps.